So in this video, I want to walk through GP18. There's two problems in GP18. Both have a known population mean and a known population standard deviation, but these cover a right side or right-tailed hypothesis test. So the first one is a development team at a small company claims their average time to fix a bug is 3.4 days with a standard deviation of 1 day. The new team manager thinks it's higher. She samples 20 bugs and the average time to fix was 4.1 days. With a significance of 5% or 0.05, do you think the manager has a valid claim? So the first step in any of these problems is to set up our null and our alternative hypothesis. So our null hypothesis in this case would be the status quo. So in this case, the status quo is that the average, or mu, is 3.4 days. The alternative hypothesis is the thing we're challenging. So in this case, the manager thought that this number was actually higher. So we can represent that by saying mu is greater than 3.4 days. Now, if we were to draw this on a graph, I will draw our graph right here. So here's our normal curve, which we're making an assumption about. And we have here our mean, our population mean, which is 3.4. So this is mu. And we're challenging, we're making a claim that this is actually, we don't agree with it. We think it's somewhere out here. We think that the whole curve is shifted to the right, and that our mean is actually somewhere over in the tail of the curve that we're representing right here. So this is a right-tailed, or single right-tailed hypothesis or analysis. So, to the second step, so we've sort of identified what our what we're trying to prove here. We've also drawn it out on a graph, so we understand: is it single tail? Is it two tail? That's very, very important. So the next thing we need to know is, what are we given? What's our given information? So our given we know is mu. That's the 3.4 days. We know sigma was given as 1 day. And we also know that there's a sample. So there's a sample of 20 bugs that was taken. And we also know that x bar, or the sample mean, was 4.1 days. And lastly, we know the significance, which is 0.05 or 5%. Now, the fact that we know mu and sigma tells us we can use a z-score. Because our population mean and standard deviation are known. So we can use a z-score, which means we can use that z-table, or the normal distribution, cumulative distribution table, table A, to get our solution here once we figure out the z-score. So let's figure out the z-score. So z is equal to x bar, our sample mean, minus the population mean, mu, over sigma divided by the square root of n, or the number, total number of samples that we took. So x bar here is 4.1, mu is 3.4, sigma is 1, and n is 20, so the square root of 20. And if you do the math on this, you should get 3.13 as your z-score. So this is our standardized score, and what that tells us is, if we were to draw this on a scale of 0, 0 being in the center, that we're negative 3.13 standard deviations to the left and 3.13 standard deviations to the right. Now, we need to go to table A now, and I don't have this on the video, but hopefully by now you know how to look this up. But if I look up 3.1 on the Z column, and then I go over to 0.03, you should get to 0.9991. Now, the 0.9991 is not what we're looking for. The 0.9991 is this, all of this stuff to the left. We want the stuff to the right. So what we have to do to get that is we subtract, I'll do it in a different color so you can just see, we have to subtract that number from 1, which will give us 0.0009. That gives us this right here. So, so the 0.0009 is essentially 0.09 or 0.09%. That's what that represents. So this is essentially saying 0.09% is what's represented there. So now our last step is we need to compare. So I'll do this in sort of what we learned back in grade school. 0.0009 is what? Is it less than, greater than, or equal to 0.05? And the answer you should get is it's less than, much, much less than 0.05. And because of this, we reject our null hypothesis. In other words, yes, it is a valid claim to say that the manager, that the average time it takes to fix a bug, there is enough evidence to make the claim that it's higher than 3.4 days. That's what that means. The second problem, and what I need to do is erase this board. So let me just erase it. And now I'm going to bring in the second one here. So here's our second problem. Our second problem is a drug study. So a recent drug study claims that the new drug cholestanderol, and that's a completely fictitious drug, by the way, it reduces cholesterol levels by 15 milligrams per deciliter with a standard deviation of 3 milligrams per deciliter. You think it's higher. This is critical, right here. You conduct a study of 36 patients using the drug and find the average cholesterol levels were 16.3 milligrams per deciliter. That should say were reduced by 16.3 milligrams per deciliter. What can you say about the drug study? And let's assume here a 5% level of significance, which is a 0.05. Alpha is 0.05. So again, the first thing we want to do is we want to set up our null and our alternative hypotheses. Our null hypothesis is that mu is the status quo, which is 15 milligrams per deciliter. Our H sub A, or our alternative, is, well, you think it's higher, which means that you think that mu is actually greater than 15 milligrams per deciliter. So this is our hypothesis statement right here. The next thing we want to do is we want to just draw this out. Even if you know, you're like, oh, I know what this is, it's always a good idea just to draw this out. So this is going to be 15 here. And our argument is that it's greater than that. So it's somewhere out there. So again, this is a right tail analysis, or a one-tail analysis, as you might see it on Table C. I believe Table C calls it, and I'm just looking it up, it's one-sided P or two-sided P. It's all the equivalent, it's all the same. So my next step is to define what do I know? What am I given? So let's do that. Let's figure out what are we given. So we know mu is 15. We know sigma is 3. We know our sample was 36 patients. And we know that the sample mean was 16.3. we also know that our level of significance is 0.05. And that's always key. You always need to make sure you know that ahead of time. If it's not given, just so you know, if it's not given, assume 0.05. It's always kind of a safe bet. Okay, so just looking at this, I can already see that I have my mu and sigma are known. Therefore, I can use the z-score, or that normal distribution table, table A. So that makes things easy. So I can just compute z. So z, again, x bar minus mu over sigma divided by the square root of n to adjust for the sample. And this x bar is 16.3 minus 15 over 3 divided by the square root of 36. And if you do the math on this, you should get 2.6. So if we go and we look this up in table A, you should get 0.9953, I believe. Now the 0.9953 is this. So I just want to point this out. So that is this. So I'm color coding it. And so the red is going to be 1 minus this, which turns out to be 0.0047. And that ends up being this piece right here. Now the last step is, let's compare this to our level of significance. So this is our last step, is 0.0047, is this greater than, less than, or equal to 0.05? And the answer is it's much less than. And so we reject, as a result, we reject our null hypothesis. And that is basically all you need to know to get those two problems solved.